Welcome to another lecture of the series of modeling and analysis of DC-DC power converters. So we were discussing about isolated DC-DC converters, and we have already seen, we have started with the analysis of high frequency transformer, the magnetizing inductance branch, and the the principle of so basically the basic topology for replacing any DC-DC converter, say buck-derived DC-DC converter, by introduction of a transformer. Transformer operating at very high switching frequency, thereby reduction in the size, and we can integrate it. We can integrate this transformer as a part of as an integral part of any DC-DC converter. So till now we have seen the buck-derived DC-DC converters. Those are forward converter, push-pull converter. Now we'll see the next and the very important topology of isolated DC-DC converter, which is a flyback converter. So flyback converter is a buck-boost derived topology. Buck-boost derived DC-DC isolated converter. So and also flyback is a very widely used isolated DC-DC converter topology. The reason is because we typically have a lot of sensitive electronic devices in our household application. So basically the voltage rating or the input voltage rating of these electronic circuits vary from 5 volt to 12 volt. So in order to drive or to supply power to such auxiliary units, we need a very simplified topology. The topology of the isolated DC-DC converter. So basically, you know that why isolated why do we go for isolation is because we have to protect all our sensitive electronic circuits. So let's say as the input and output in a non-isolated DC-DC converter are directly shorted. So in case the user touches any of the live wire, so there is a chances of a shock. So isolated DC-DC converter is that gives the additional benefit of isolation between primary and secondary, as the grounds are separated. So any fault occurs which occurs on one side of the converter will not be reflected, or the user is safe from any fault in the primary side of the converter. So that's why isolated DC-DC converters are used. So to power such isolated so in order to power such switch mode power converter devices in household applications, say mobile charger, laptop charger, or any auxiliary supplies in the washing machine, fridge, television, etc., the basic topology of a power converter should be as simple as possible. So simple means the number of power electronic components should be optimized for a given requirement. Then it should be as cost effective as possible with least required number of power electronic components. So the power rating of such SMPS devices vary usually from 2 watt to 5 watt, and the voltage rating is 5 volt, 9 volt, 12 volt. And some of the loads, let's say BLDC ceiling fans, LED lamps, and the 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 RO filters which we use in our household application, the power rating of them vary from 24 watt to 80 watt, and the voltage rating is typically 12 volt, 24 volt, and it goes up to 48 or 72 volts. So even in high power applications, the auxiliary power supplies used in air conditioners like ACs, refrigerator, washing machines, keypad display, etc. So these are the auxiliary, or you can say human machine interface auxiliary units of these high capacity devices. So they also have this switch mode power conversion, and they have keyboards and display powered by 5 so the power rating is typically 5 to 20 watt, and the voltage rating is 5 to 12 volt. So that's why, as these components are widely used in household applications, we need to have a very compact design of the such isolated DC-DC converter to meet the requirements of these auxiliary supplies. And thus we have to, at the same time, we have to see that the design of the isolated DC-DC converter is very optimum, cost effective, simple, and which will have a very least number of power electronic component. So flyback topology is a very widely used DC-DC power converter topology, specially used for auxiliary power supplies used in control or powering auxiliary loads of any big application. It is also very popular in fronted uncontrolled full bridge rectifiers, EMI filters, supplying power to fuse, MOV, lighting, etc. So we'll see the topology. The topology of flyback converter looks like this. So till now we saw that all DC-DC power converters were having a transformer, a tightly coupled winding, primary and secondary winding. Now before going to the topology, we'll see the principle of coupled inductor. So in a coupled inductor, there are two windings wound on a same core, magnetic core. Say this is the toroidal magnetic core, and this is a winding. This is inductance L1. This is with inductance L2. Say that this is powered with a supply of V1 and this is open circuited, and this number of turns is N1 and here it is N2. So this is a toroidal based coupled inductor, or we can have a EE core. In a EE core, what can happen is the coupled inductor can be wound on the same core like this. So this is L1, this is L2. So these are the coupled inductors. So we know that L is equals to N square by reluctance, and reluctance was length of the magnetic path divided by relative permeability of the material into area of cross section. So we can say that L is directly proportional to N square. So if you were to relate the inductances, what we can write is L1 by L2 is N1 by N2 whole square. So this is the basic relation of the coupled inductors. Now this I also forgot to give a dot polarity. So the overall the basic overall inductance formula, overall inductance L equivalent for this circuit is L1 plus minus L2 plus minus M, where M equals to K under root of L1 L2. So K here is called as the coupling factor. K is the coupling factor. So K is 1, which means that the coils are tightly coupled. This is the case with transformer. And K is less than 1 for a coupled inductor. So based on the dot convention, here we can see that the equivalent inductance is L1 plus L2 plus minus M, where M is K under root of N1 K into square root of L1 L2. So as the windings are not tightly coupled, the coupling coefficient is not unity. So that's why it happens. So say that this is the current I1, and this is, say that the current I1, here the convention is that at the dot the current is entering. So this is I2. So I2 is 0 in this case because there is no supply. So the overall inductance will be in this circuit, overall inductance C net primary L equivalent, C net primary will be L1 only because I2 is 0. So what happens when we simultaneously supply, this is V2, supply this coupled inductors using two supplies. So coupled inductor we can again define represent using a transformer. So say that it's, as we are dealing with switch mode power converter, so let's assume that the primary and secondary of this coupled inductor are excited by different voltage supplies. This is V1, this is V2, this is N1, this is N2, this is S1, this is S2, this is I1, and this is I2. So here what we assume is that till now for the forward and push-pull converter, for the secondary, the I2 used to be coming out of the dot, but now the convention for a coupled inductor is that the current is entering the dot even in the secondary side. So this is nothing but the coupled inductor. These are the coupled inductors, and we are seeing the analysis of this circuit for the coupled inductor. The assumption is that not like we want to see how the magnetizing branch behaves. So in this circuit, what you see is that there is no so basically there is no path at the primary for the magnetizing current or for the core to demagnetize. So that's why we are having another source V2 connected through a switch S2 at the secondary side. So our aim is that to reset the core, at least in one quadrant. So our aim is to magnetize and demagnetize the core. This is BH curve. Assume that it is almost linear. So our aim is to magnetize the core in one cycle and then demagnetize the core. So there has to be some circuitry to do this demagnetization. When S1 is on, the primary side is powered and the current I1 increases. So this is the LM branch and this is the current I1. This is the current I2 dash. So as in the secondary side, the current is entering the dot. So the I2 dash also, the current will be entering the dot. So it is I2 dash. And this is the current IM. So in this case, when S1 is off, so this magnetizing current should have a path to flow or to demagnetize or to reset the core. So basically what we'll do is we'll operate S2 in a complementary fashion. This will make sure that whenever S1 is off, the S2 will be on. If S2 is on, what happens is the our aim is to reset the core. So when S2 is on, the current IM should decrease. It will decrease when I2 dash will increase. There is a mistake in this thing. The convention, this convention of I2 dash. So as I said, that it enters, this current I2 enters the dot polarity. So that's why it should be like this. So if we apply KCL, it will be IM will be D into I1 plus 1 minus D into I2 dash, where I2 dash is I2 into N1 by N2. N1 by N2. Okay. So we don't have any means of representing this currents I1, I2 in terms of any known currents like inductor current or magnetizing current. So basically we are representing magnetizing current in terms of I1 and I2 only. So S1, we say that S1 and S2 operates in the complementary fashion. So basically when S1 is off, then S2 will be on, and the current will flow in such a way that the core is demagnetized. So in this case, when this is off, when switch S2 is on, the current I2 dash will be developed. The reflected current of I2 dash will come here. So The thing is that in a transformer, whenever we supply when we excite the primary winding using a voltage source, voltage is the flux will flow through the magnetic core, which is a variable flux. This rate of change of the flux will induce an EMF across the secondary, and that induced EMF will always try to oppose its cause. So that's why till now what we saw is that in the secondary side, the current the current I2 in the secondary side used to flow out of the dot, and as this current opposes the primary, or the reason of the induction of the EMF, so its reflected component in the primary used to flow into the dot. Similarly, in this case, what we'll do is, in this case I2 is flowing inside the dot for the secondary, so for primary it will flow out of the dot, so I2 dash. So when S2 is on, when S1 is on, and when S2 is on, when S1 is on, I1 will be Im and I2 will be 0. So in this case, this is Im, this is equals to I1, and this is T. So the current Im will increase, or the core is magnetized. When S2 is on and S1 is off, in that case what happens is that Im equals to I2 dash and I1 equals to 0. So this results in again the core magnetizing. So but our aim was to reset the core. So what can be done is, we have to change the direction of I2, or basically we have to build the flux in the other direction. That should be the case. So to demagnetize the core, either reverse the secondary dot the dot polarity, or reverse V2. So in that case what we'll do is, this will be the case. So what will happen is, now in this case the secondary current is moving out of the dot, so its reflected component will go inside the dot. It will be like this. So therefore, thus when S2 is on, then the magnetizing current Im will be equals to what? Minus I2 dash. So in that case, the core will demagnetize. This is equals to I2 dash, this is T, and this is Im. So the basic aim of a coupled inductor and to show the switching action of both primary and secondary is that the magnetizing current or the magnetizing flux is continued using this coupled inductor effect. So if in this case, if the inductors were perfectly coupled just like in a transformer, then opening of the switch S1 will not have caused any impulse voltage generation. This is only when if S2 provides a path for the current I2, where I1 and I2 will provide the flux continuity. So in this case, the flux is continuous. The flux is continuous. If the flux was continuous, so thus there are no peaks. Aren't peaks in voltages. So what happens is, when S1 is open, means when S1 is off and S2 is on, this will make the current I1 to 0, and immediately it will make the current I2 to rise. Then and its component in the Im will be its reflected component I2 dash. So in this case, the energy is stored in the magnetic core. The energy is not stored in the coil. So when the switch S1 is on, what happens is, from the source the core gets magnetized, and when S1 is off and S2 is on, in that case the magnetizing current demagnetizes through the current I2. to the load side current. So this we can replace by the load side. So the whole idea to show this switched coupled inductor network is that till now what we saw is that in a perfectly tightly coupled inductor system, say in case of a transformer, where our aim was to make this transformer an integral part of a DC-DC converter, what we used to do is we used to reset the core. We used to set and reset the core. In forward converter, what used to happen is it used to operate only in one quadrant of BH curve, that is in the first quadrant. That is, the current used to rise in one direction and fall in that direction only. It never has to change its sign in a push. So in order to further utilize the core area, what in push pull converter used to do is that we used to do in push pull converter. So this was the waveform in the push pull converter of the magnetizing flux or the magnetizing current. This converter used to operate in two quadrants of pH curve, that is the first and the third quadrant. So first the current used to rise in one direction, then fall in that direction, then rise in the opposite direction, then fall in the opposite direction. So basically this push pull used to operate in this fashion. BH curve. First it used to the IM used to rise, then used to fall, then used to rise in the other direction, then again it used to go, and thus this was the case. And to demagnetize the core, what it used to do is that there used to be a provision in the primary side for letting this IM current component to be continuous, as well as it was able to demagnetize the core. This is through the primary side only. But in a coupled inductor system, what happens is that in a non perfectly coupled inductor system, so basically it can be a perfectly coupled system also. So this coupled inductor can be a transformer also. That is a different thing that we'll see how the transformer for a flyback converter is to be designed. But the whole idea of doing this thing is that here the core is demagnetized by the secondary side, that is by the load side. So because the reflected component of load current is seen in the primary side, or what you can write in this case is IM. So in this case, when S1 is off, IM equals to minus IM. So in this case, this IM is to flow like this. You can say that because IM is equals to minus I2 dash when S2 is on. So basically, if we see how, so we used to see the reflected component of I2 on primary. Now we'll see the effect of the reflected component of IM in the secondary side. So in this case, IM is to flow like this. Or what you can see is that if we replace V2 with a load, so what you can say that IM equals to load current, IM equals to I load, and that's how the core is to demagnetize, to maintain the continuity of the magnetic flux or the current, magnetizing current. So this is the idea of a basic idea or basic working principle of a flyback converter. Flyback converter means that here in this case, when the core is to reset, the magnetizing current component equals to the load current component, and the core resets using the load current using the secondary side. So to derive a flyback current topology, what we can do is topology of flyback. What we do is that S2 a diode D, say D1, and V2 through a load plus capacitor. Now we got the idea of how the circuit will operate, and S1 is a normal device. So if I'll draw the topology of a flyback converter. With the magnetizing branch. So what we do is that we replace S2 with a diode. Whole idea is that diode used to conduct the current whenever the switch is off. So say that, so then we'll see how to place anode and cathode of the diode. This is, say, V in. Plus minus. So when S1 is on, the voltage here plus polarity comes here, and thus the voltage induced here will be plus minus. In that case, the load current should be 0. And when S1 is off, then the load current is to flow. So basically what we should place is that we should place anode here and cathode here of diode D1, because diode D1 and S1 should operate in a negative fashion. And then we have a load. This is I load, this is V0 plus minus, this is C, this is IC, and this is ID1. We just replaced it, nothing is there. Now, okay, this is N1, this is N2. Now very basic question arises in our mind, that where is the inductor in this circuit? Where is the energy storage element? So the inductor is here only. This is the tightly coupled inductor. So the energy storage element, one is the capacitor that is already present. Where is the inductor? Question is, where is the inductor? The inductor is here only. That is nothing but a tightly coupled inductor. So this is the Flyback converter. So in a Flyback converter, it works on the principle of a coupled inductor. It can be loosely coupled or it can be tightly coupled, which means that it can be coupled inductor, means two coils wound on the same core, or it can be transformer also. Yeah, basically transformer is a very tightly coupled thing. The winding are wound tightly one above the other on the same core. But to show the strongly coupled inductor, we can wound the two coils on the same core at a distance. So that is the idea of a Flyback converter. So in a transformer, what happens is that energy instantaneously transfers from primary to secondary using the load current component I2 or I2 dash. So in transformer, the magnetizing components are assumed to be very small, because the reluctance path of the magnetic path is very small, and we use a very high permeability material. So in the transformer cases, when say in the push-pull or in the forward converter, we used to neglect the magnetizing currents mostly, because the magnetizing current, whichever analysis we saw till now, the current of IM will not, so basically the contribution of IM in the other currents like inductor current, ID3 current, ID4 current, in all these currents is, there was no contribution. But in a forward converter, IM contributes to the load current. So that's why magnetizing current we should not ignore in this case. So in this case, in the case of coupled inductor, what we assume is that, which we already have seen in here, this switched coupled inductor thing, is that the energy stored in the magnetic core instead of the coil. The energy stored in the core, and it is stored in the core when one winding is excited while the other is open circuited. So when S1 is on, S2 is off, and when S1 is off, S2 is on. That is the assumption. So basically, in this case, the switch coupled inductor, the flux continuity is maintained. So now we'll see the operation of a Flyback converter during the on state. So case 1, when S1 is on, what happens in this case? I'll draw the magnetizing path also. After this, the switch is on now. So it is like this. So S1 is on. This is the current, say I1. So what happens is, the voltage applied here is V in, plus here minus here, so the dot is positive. So here V in into NS by NP. Say this is NP and this is NS. This voltage is induced here with positive here and negative here. So the negative voltage is appearing across the anode of the diode. It will never turn on. So it is off. D1 is off. And here S1 is on. And thus, okay. Like this I will denote. So what happens is that the capacitor, which is, we'll assume that it is pre-charged, it provides power to the load. So in this case, for S1, Vs1 is 0. V primary, that is the primary winding voltage, primary allied winding voltage, which is equals to V in. Vs, that is the secondary, okay, secondary winding voltage is what? V in NS by NP. So IS1 is equals to I1. So in this case, this current, which is the diode current, ID1 is 0. So in this case, this is ID1 is 0. So again, this is ID1 is 0. Here current is entering the dot. So the reflected current component should leave the dot. So it is I D1 dash. Okay. So I1 plus ID1 dash equals to IM. But ID1 dash is 0. So I1 equals to IM, which is equals to IM. So IM flows like this, and this current flows like this, because this is open circuited. So S1 is done. Now we'll do for the diode. Diode is off. So what is the voltage drop across the diode? The voltage drop across the diode is, so this is plus, this is my V anode cathode. So plus minus, plus minus, plus minus. So voltage drop across the diode is minus of V0 plus V in NS by NP. That is V0 minus of V0 plus V in NS by NP. And ID1 is 0. What else? IC becomes equals to minus I load. Only when the switch is on, then IC equals to minus I load. And when it is case 2, that is when S1 is off, what happens is, So okay, what happens is D1 is on and S1 is off. So in this case, this is the I1 becomes 0. So in this case, ID1 becomes equals to IC plus I load. So in this case, this is again ID1, current entering the dot, so here the current should lead the dot. So in this case, IM is equals to I D1 dash, that is NP by NS into IC plus I load. So here also we saw that magnetizing current includes the load component, and when it is off, when it is on, IM equals to the input current basically. So the current rises because there is an inductor LM and the rate of rise of current. So it is basically, it is like this. This is IM, this is T. So basically this slope is V in by LM. And in this case, when S2 is off, IM equals to the load component. So when it is off, voltage drop across, this will be what? V naught, with plus above and minus below. So what is the voltage drop? What is the voltage induced across the primary? This is again V naught with plus below and minus above. So dot is minus, so this is minus, this is plus. So in that case for S1, what is VS1? Minus plus, and say this is plus minus. So VS1 is what? V in plus V naught. There is a voltage which is to be blocked by the device S1, and IS1 will be 0. For diode D1, VD1 will be 0 or it is 0.7, that is the on state drop. We'll typically ignore it. Then ID1 will be IC plus I load. So again it is load dependent. So in the on case, the input is supplied across the primary of the coupled inductors and the core is magnetized and the load is not connected. When the switch is off, the input is disconnected from the core and the core demagnetizes and supplies its power to the load. So it is very much similar to a buck boost converter. So what a buck converter does is that when it switches, a normal non-isolated buck converter, what it does is that when the switch is on, the source as well as the inductor supply power energy to the load. And when so basically and in the case of a boost converter, when the switch is off, the source and inductor supply energy to the load, and vice versa in a buck boost converter, and vice versa. But in a buck boost converter, when the switch is on, the an inductor is in the parallel branch between input and output is magnetized, and when the switch is off, the input is cut from the inductor and the inductor demagnetizes. So basically it mimics the characteristics of a buck boost converter. Same is the case with the flyback converter. Now we'll see the operation of a flyback converter for continuous as well as discontinuous mode. So as I told you that this couple inductors, this switch couple inductor thing, the switches are switched in synchronization so that the flux component will be continuous. So we'll see the steady state operation of a flyback converter with continuous flux mode of operation. We'll see this mode of operation of the flyback converter. So first we'll see the switching pulses. Or here simultaneously side by side we'll see the continuous as well as the discontinuous mode of operation. So here we give the gate pulses. This is the gate pulses of S1. So first we see the continuous conduction mode of operation. Then I'll draw the flux waveform. So in this case, the assumption is that when S1 is on, it is the core is magnetized, and when S1 is off, it is demagnetized. So it will be like this. And it will be falling in this fashion. So it is a continuous mode of operation. So whenever we used to decide that whether a DC-DC converter, a non-isolated DC-DC converter is in continuous or discontinuous mode of operation, we used to see the inductor current. Because based on the switching action, the inductor is to charge, means to get magnetized using the supply or give the power to the load. Based on that, we used to see. So in this case, we'll say that the mode of operation of this flyback converter, because as the inductor is integrated in this copper inductor thing, this transformer thing, so we'll decide the continuity of its operation based on the IM current. So this is IM or phi m, both. So it is continuous. So what else? We'll draw the waveform of the switches and the diode. We'll draw the voltage across the primary winding, or VP, we'll say. Yes, VP. When the switch is on, VP is V in, and the switch is off, VP is minus V naught, because the dot polarity is positive. So this waveform belongs to VP, where this is V in and this is what? This is not V naught actually, there is a mistake here. This is V naught into NP by NS. V naught NP by NS. This is the voltage drop across the voltage across the primary winding of the transformer. Now we'll draw the secondary voltage component. When the switch is on, the voltage across the secondary is V in. We'll assume that the convention is the dot, that is the dot one is positive, or we can say that the convention is like this: Vs plus minus, and Vp is like this. Vp is like this, plus minus. So as per this convention, Vs will be minus of V in Ns by Np. So V naught and V in can be greater than or less than equal, so that we don't know. So this is V in Ns by Np, and when the switch is off, the value of Vs is V naught. But in this case, what happens is that there is a MOSFET, there is a device here, say it is a MOSFET. So MOSFET has stray capacitances C, GD, C, DS, and C, GS, GD, GS, and DS. And the leakage, so basically this is a transformer. The flux is linked with primary and secondary. So there is some component of leakage. So we can assume it to be the leakage LL. This is the leakage component. So this leakage component of the flux, what happens is and here there is a stray capacitance, say it is CDS. So what happens is it's a series thing happening. So this is Vp and this is V in. So this is LL and this is CDS. This is basically a MOSFET device. So it is a tank circuit. So in the voltage there will be the Vp. So Vp will have like this spikes due to this LC resonance. So this will result in resonance. So leakage is not in your hand. So we'll see later the design of the transformer for a flyback converter. But due to this oscillation, there will be some oscillations across the seen across the primary voltage. So I'll draw the primary voltage like this. So this effect is called as the ringing effect, where the leakage component of the flux reacts with the DS stray capacitance of the device. So similarly, reflected component of this can be seen in the secondary voltage. So this waveform belongs to Vs. This is the ringing effect. The voltage when it is off is what? V0. This is V0. Now we'll draw the currents to the devices. Now we'll draw the current through the switch IS1. When S1 was on, the current in IS1, so basically IS1 was IM, and IM is drawn here. So this is IM, this is IM, and when the device is off, I1 IS1 will be 0. So it will be 0 like this. So this is IS1. Now we'll draw the diode Okay, we can draw the diode voltage here only. So basically this ringing effect will be seen across um, the voltage across the diode also. When the switch is on, the diode is off and the voltage across the diode is what we have written here. Vd1 is minus of V0 plus V ns by Np, and it is 0. So this ringing effect is not here. So we can denote it like this, then 0, then again negative, then again like this. The value of this component is what? V0 plus V ns by Np. V in ns by Np minus, and this waveform is Vd1. So if we draw the current through the diode in this case is off, the current is 0. In next case the diode is carrying some current that is equal to the load current. Yes, the current equals to load current. So here what we can write is that it is the current is there when it is off. So we can write 1 minus d into id1 is equals to ic plus I load. This is the generalized expression for the secondary side current, the KCL across this node. So what happens is, in this case, when the device is on, so the inductance is present here and then there is a diode. So it's this section can be called as a boost section because it's a buck boost converter, and this is the buck section. So it's a buck boost converter. Because we saw that when the switch is on, the core is magnetized and the load is disconnected from the supply. When the switch is off, the input is disconnected from the core and the inductor or the core demagnetizes using the load. So this is very similar to a buck boost converter. So the secondary side or the output side is also looks very similar to a boost converter. So basically in this case, when it is off, the diode current is like this. It is like this. This is ID1. So in this case, when s equals to 2, I forgot to draw the basically. So in the boost converter we used to draw this current ID as 1 minus d into IL, but here in this case we don't have IL, we have IM, that is on magnetizing current. So in this case, as we have seen, to transfer this this switched couple inductor thing, so IM was flowing in this fashion like this. So similarly I'll draw the component of IM in this. So this is ID1, this is IM. So IM is like this. So this is equals to IM. So in this case, which is equals to IM. So this is IM. This is the ID1 current. The same thing if we draw similar waveforms for the discontinuous mode of operation. In that case, So in that case, the assumption is that this flux rises to a value and falls before even the start of the next cycle. So this is Im or phi m. This is whole T switching, and the time for which S1 is on is into D into T switching. So this is T switching, and this is capital D into T switching. Similarly, we can have a D dash here. So this is D dash into T switching, and this whole is 1 minus T whole into T switching, and then thus the remaining time is 1 minus D minus D dash. This is 1 minus D minus D dash into T switching this time. So again we'll draw the waveform of the voltages. So we'll draw Vp. When the switch is on, Vp is again this value, V in. Ringing effect, V in. It will fall like this. Then again it will rise, ringing effect. Okay. So how will be the, just a second. Okay. So when S1 is on, it is Vp is V in. Now when S1 is off and when the phi is falling, then it is minus V0. So it is, this is V in, this is V0 NP by NS. Then what will be the value of this voltage when there is no flux in the component? So in that case, Im is 0 and the switch is off, S1 is off. So when S1 is off, I1 is 0, and when Im is 0, then the capacitor provides momentarily the power to the load. So ID1 becomes 0. So Im becomes 0 in that case. So when Im becomes 0, the diode is also turned off. So the case 3 will be, okay, this is the case 3, that is only for discontinuous mode. In that case, it is like this. This is V in plus minus, this is I in or I1, then diode and the, we don't know how the diode is there. I'll draw the capacitor and the load. This is I load, this is IC, and this is ID1. There is no Im. So this is Im equals to 0. So Im becomes equals to 0. No current is flowing. So there is no motivation for this diode to turn on, because input side it is turned off. This is turned off. S1 is turned off. Here also it is turned off. Why? Because there are two reasons for diode to turn on. First is the voltage across it, and second is the for freewheeling the inductor current, or for freewheeling any current which can't change suddenly. In this case, both of them are not possible. So in this case, S1 is off, and the that D1 is also off. So M is 0. So both are off. So in that case, what happens to the voltage across this is that, say that it transitions now from case 2 to case 3. So in this case, what happens is the voltage across primary was negative. Then so before that, analyzing that's it, let's complete all the steady state waveforms of the continuous mode. So I think in primary side we have done all the waveforms: voltage across primary, voltage across secondary, voltage across the device, current to the device, voltage across diode, current to the diode. Then I think we should go to the secondary side, that is the capacitor and the load. So the load is constant in all the cases, that is like this. IOD is constant with respect to time. So as we know the waveform of ID1, we can know the waveform of IC. Out of ID1, the average value goes to load and remaining ripple goes to the capacitor current. So this is ID1. So if I draw IC, it will be like this. It will be like this. This value is I load, and this waveform is IC. IC is there, so V0 we can draw. V0 will be like this. IC C dV by dt. So V is 1 by C integral. Integral of a negative term is a constant falling term like this with a slope, with a straight line slope. And integration of a falling slope is a falling polynomial, which is like this. Then again a constant term will be like this, and again a falling polynomial. This will be V0, the expression of the waveform of V0, and it has its own average value, that is V0. So this is the steady state analysis of the flyback converter in the continuous conduction mode, which is done. Now we'll see our concern was to see how the converter reacts in the third case, that is when there is no flux, and how does the voltages change. In this case, say that the converter switches from case 2 to case 3. That is, initially there was some IM current. Now suddenly the load was not sufficient. So basically here again I M minimum will be less than, so basically IM minimum will be less than 0. That is the function of magnetizing current. So there can be two reasons for discontinuity for flyback converter. First is the load, second is the LM value of LM, that is the transformer design. So we'll see it. So in this case, what happens is that the primary current it rises suddenly. And again goes to its value of V in, and the Vs, for Vs it is like this, rise, become this value, it will fall below the 0. Then again rise to positive value, then again goes to this value. Now I'll tell you the reason behind this nature of the graph. This is V in ns by np, and this is V naught. This waveform is Vs, and this waveform is Vp. So what happens is that the voltage across the transformer terminals suddenly falls, because in this case the magnetizing component is 0. The dominant component is the leakage component, that is, this is Ln, this is C ds. So leakage is the part of the total flux of the circuit which is not necessary or which is not useful for building the flux in the secondary, so that the voltage is induced. So in that case, what happens is, due to this ringing effect, the voltage is seen across the primary, that is, say this is Vp plus minus, and this is Vs plus minus. In that case, what happens is, due to this ringing effect, the voltage across the primary will suddenly shoot up, and similarly the voltage across the secondary will also shoot up, but in the other direction, because the polarity is reversed in this case. And then again it will go and reset to its original value, because now whatever is the current drawn in from the primary, that is used only for taking care of the leakage component, because the magnetizing component of current is 0. So it's a resonant tank circuit. In the resonant tank circuit, what happens is that so basically Vp is connected in this fashion. It is like this. Vp, and this is Ll, and this is C ds. V in plus minus. We can do the Laplace analysis, the steady state analysis of this circuit in S domain, and then we can find the response of the Vp in the time domain. So based on this, we saw that due to this, so basically assuming that there are no losses, so basically it's an undamped system, but ultimately the wire will have some resistance. It will be it will have some resistors like this R. So the oscillation will be damped oscillation. That's why Vp and Vs will be of this nature. Similarly, if we draw the waveform of the this thing, diode and the switch voltage and currents, what we saw is that and yeah, I forgot to draw VD1. So VD1 will be like this. I will draw this, then 0. This will be minus of V0 plus V in ns by np, and this will be 0. Again, as Vs is Vd plus V0 minus plus Vd1 actually minus. So Vs is Vd1 plus V0. So Vd1 is Vs minus V0, and Vs is of Vs is of this polarity. So Vs minus V0. We assume that V0 is constant. So it will be also of this nature. Some average value is subtracted from it. So it will be like this. Again it will be across this value. Okay. Then deposit again this value. Again it will be 0. this is VD1. Okay. Now if we draw the waveform of IS1 and ID1, in that case what happens is that this effect of the ringing will see its effect on the currents on IS1. So in this case, as the state component of DS is outside of the MOSFET, so IS1 is still 0, and as D1 is off, its effect on the current will be negligible. So the waveforms are very similar to the previous cases. So IS1 will be IM, IS1 will be IM in this case when it is on, and in the other case it will be 0 for the whole period. This is IM and this is IS1. Now for ID1, in the negative time it will be IM. ID1 will be IM. Yes, ID1 will be IM. I think here I did a mistake while drawing the yes, this is IM. Then here in this case this will be like this. Then again 0 falling. This is IM, and this waveform belongs to ID1. Like this. Actually, I think this is not IM. This is IM into N P by NS. So it will be like this. Okay. This is IM NP by NS, and this waveform is ID1. So now the last waveforms. So waveform of the capacitor. Okay, it is like this. This is IC, and this value is I load. Then V0 will be constant value is like this. Then it will be like this. Then again this is V0. So this is the steady state analysis of the flyback converter in continuous as well as discrete continuous mode of operation. So we saw that there is a ringing effect due to the leakage flux, and that is nothing but the resonance effect of the leakage component and the CDS. That's why its effect occurs at the beginning of the change of the voltage. So whenever the polarity of the voltage, so whenever the state of the voltage across the device changes, at that time we'll see the ringing effect. So we can't control CDS, so we can have a control over the leakage component. So basically the ringing effect will be overcome, or it will be reduced by the transformer design. So similarly we can do the volt second balance of the inductor. So here in this case we have to do the volt second balance of the winding, volts second balance only for CCM. So this is CCM and this is DCM mode of operation. So volt second balance we have to do it for the transformer. At the transformer, because it's a coupled inductor. So if we do it, the voltage, we have to see the voltage across the either primary or secondary. We have to do the volt second balance across the primary or secondary. So in this case, when the switch is on, Vp is V in when the switch is on, and when it is off, it is minus V naught of Np by Ns. So V in into D into T switching equals to what? Equals to V naught Np by Ns. Np by Ns into 1 minus T into T switching. So V in D equals to V naught Np by Ns into 1 minus T. So that's why V naught is V in into D by 1 minus T into Ns by Np. This is the volt second balance of the, and this is the steady state equation of the flyback converter. So the flyback converter is a buck boost derived converter. So if you want to write flyback converter as a buck boost converter, what we can do is that flyback as buck boost derived converter. So a basic flyback, a basic buck boost is like this. So if we draw flyback as well as the buck boost converter, left side is the buck boost converter where V naught is V in by 1 minus T. Here is the inductance L, and here if we redraw the flyback converter which resembles a buck boost converter, so here we can see that using the same dot polarity, the secondary side is similar, the primary side is similar. This portion is the inductor section. So this inductor is this transformer, and now I'll not draw the magnetizing branch. Okay, this is the transformer. So say that it is Lm and it is Lm dash. So we have to refer this to secondary. This is referred here. Therefore here L becomes Lm into Ns by Np whole square. So flyback converter is nothing just like a isolated buck boost converter where the inductance is replaced by Lm into Ns by Np whole square. So ultimately what volt second balance is the flux balance. So that's why we applied the volt second balance across the transformer, not the inductor, because here we don't have inductor. It's nothing but the coupled inductor thing. Now there is one more advantage of the flyback converter is that it can be implemented to multi-winding transformer where the secondary can be multiple windings. say that your SMPS application needs multiple supplies with multiple grounds. So the secondary circuit can be floating. That is, it is not sharing any ground with the primary circuit. So the user can, so any user can adopt any terminal as the reference for the output. So the advantages of Flyback converter is it is a small and compact isolated DC-DC converter with only only one switch and without an inductor. The inductor is nothing but the coupled inductor or the transformer. It can have multiple outputs with multiple grounds. So those multiple secondary windings along with the diode and the capacitor. It's a buck-boost related topology. So that is advantage, means you can have more or less voltage, that depends on your application, and there is no additional inductor required. So basically now comes the design section. How to design the flyback transformer. We know that the design of flyback transformer should be like this. Transformer design for flyback. So the working of the transformer in flyback is that the energy is stored in the core during the switch is on, and when the switch is off, the core demagnetizes using the load. In that case, the load current is the magnetizing current. So the flyback transformer is designed to store energy in its magnetizing inductance, in the magnetizing, not the leakage. So hence, in order to increase the LM, so air gap is added. So here energy is stored in LM, magnetizing component. So for the given material, say we already have set the core material for a given material, and it is a high frequency transformer because it's a DC-DC converter, a SMPS based converter. So we will use a ferrite core. I'll first select a core. The advantage of ferrite core is that the maximum flux density is 0.2 Tesla, and we'll need only small number of turns to get the desired inductance. So once the core is selected, what we'll do is the inductance we have to select. So inductance L is N square by reluctance, where reluctance is L by mu A. So what happens is the reluctance, what happens is if you want to get the desired LM based on the circuit design, so the reluctance, what we'll do is we add a air gap. So there is some air gap like this. So this is a circular cross section. This length of air gap is L1, and this length of air gap is L2. So reluctance equivalent will be reluctance 1 plus reluctance 2, that is L1 by L1 is the material, so it is mu naught mu RA plus L2 by mu naught A. So as this for the air, as mu R is very high, very much greater than mu naught, so reluctance equivalent will be almost equals to L2 by mu naught A, which is high. So reluctance will be N square by L2 by mu naught A. So that's why this inductance we can get the lower value of inductance or higher LM. Because what happens if we have add a air gap is if the air gap is added to the magnetic core, this increases the MMF, that is the NI, number of turns into the current, MF of the, so IM into N for the rated flux density of the core. Once the core is rated, the flux density is fixed, and in order to increase the reluctance, we add a air gap. So that will result in need more MMF, and thus it will need more IM. If it needs more IM, oh okay, I have written a mistake here. if it needs more IM, it will need less LM. So that's why this is mathematically proven that LM is less compared to the previous LM without an air gap. So thus flyback transformer is done in such a fashion. Ferrite core is selected. The new point is there. We need a more magnetizing current because the requirement is the more MMF, and thus by addition of an air gap we get the more MMF or the less inductance or the less LM. Less LM means more IM. So in this case we saw that the leakage flux was there, and the leakage flux component used to just discharge. So basically the leakage flux component used to be wasted, and you cannot avoid it because you can't make CDS 0 and you can't avoid LL. So if you want to make use of the energy in the leakage component, we should have a circuit provision to pump the energy due to the leakage component back to the source, just like we saw in the forward converter. So the energy in the leakage inductance needs to kill in the primary circuit using a damping diode. Either we can use it for supplying power to the source, or as this leakage component is creating problem in the voltage across the devices as well as the voltage across the windings of the transformer, we have to take care of it. So in order to take care of the leakage component, what we can do is to reduce the ringing effect, due to leakage inductance LL, what we do is additional diode is added, or we add a RCD snubber. We add an additional diode, or we add a additional clamping diode, or we add a RCD snubber. So how to add additional diode is that this is the leakage LL, this is the magnetizing branch, this is the thing. I'll draw only the primary side, secondary side is same. So this is LM. What we do is first we'll add a diode like this, but in order to further reduce the fall of the current, we should have a zener, as we discussed in the previous section of the forward converter. So this is the IM which used to demagnetize using this circuit. So this is the clamping diode. And this is B in. This is by using of the clamping diode. Or if you want to use a snubber, we can use the RCD snubber parallel to primary winding. But what happens is, we saw the effect of the leakage component in the voltage across the primary, secondary, as well as the voltage across the switch. So to protect the switch, we need additional snubbers. We need additional snubbers for the device also, device and diode too. So that is RC snubber. So the by doing all the modification, what we get is that this should be the circuit of the device by incorporation of the snubbers. Say it's a MOSFET like this, it will be So this is gate, drain, source. This is V in minus plus, this is leakage, this is I in, this is LM. So we have a snubber. We'll have a diode just like what we saw there. Then we have a damping component and a capacitor. This is R, C, R1, C1, T1. And across the device also we should have a this thing. So this will be R2, C2. Similarly across the secondary side, if we have a diode, we should have a RC's number. So this diode, we'll call it as D1, then this will be D2, this will be R3, this is C3. Similarly, if we have multiple secondary winding, we can just repeat the secondary circuit like this. So this is the snubber circuit. For snubber is for dV by dt protection of the devices and the diode, which I already discussed in the previous lectures. So to avoid that, we should have a series combination of RC in parallel to the device to protect it from the dV by dt damage. Similarly, to take care of the leakage component or to reduce the leakage component, we have to have a RCD's number across the primary winding of the transformer. So we will stop here. In the next lecture, we'll see the other topologies of the other topologies of DC-DC isolated converters, which is half bridge isolated DC-DC converter and full bridge converter. Thank you.